Our next lab is an exploration of inclined planes. In the lab, we'll use the Logger Pro program on the computers. With the motion sensor already connected, it should pop up with two graphs, a position time graph and a velocity time graph. If it does not, there are directions in the lab sheet telling you which file to open. You'll be using the physics books to prop the ramp at different angles. We're going to use 1, 2, and 3 books for each variation of angle. Make sure that the ramp is set up so that it ends at the bottom at the side of the computer, and that the plunger is out on the cart facing downhill toward the computer. That way it won't crash when it hits, it'll just bounce. Use this angle finder, set it on the ramp, and determine the angle. The angle will be different for each number of books used in the stack. To collect the data, you'll click the Collect button on the program on the computer, then have someone release the cart from the top of the ramp, and then after it reaches the bottom of the ramp, click the same icon, which will be red, to stop the data collection. You'll have two graphs that look similar to this. You're going to need to highlight the slope on the velocity time graph. We've done this before. Click and hold the mouse and drag it to the right so that it highlights this same area. You need the straight section that represents the cart accelerating down the ramp until it stops. Do not collect extra data off this graph. It's important that you highlight the same area as I've shown in this video. Next, we do a linear fit of that slope so that the computer will tell us the slope and we don't have to calculate it. We've used this linear fit icon before. There's a picture of it in the lab sheet, and I show you here that it's the fourth one over from the Collect button. With the correct area highlighted and then clicking that linear fit icon, a box will pop up that shows you the slope, m, which will be the average acceleration for the cart. You'll write this number down in your data table. You'll also be calculating acceleration to compare. You're going to need the weight of the cart. The cart is equipped with a very strong magnet in the back side. If you will gently suspend the cart over the table using the green spring scale, you should be able to get the weight of the cart in newtons. If you mess around, the cart will drop off, which might damage the cart, so just be gentle and get your data. This is not a time to mess around. You also are going to need to determine the force of friction. It is a friction, not quite completely frictionless, but there is less friction on this cart with these wheels, but there's some. So use the magnet again on the back of the cart. Suspend the cart in the middle of the incline, and then read on the spring scale how many newtons are recorded. This will be your force of friction for your calculations. In the lab, you'll need to draw the free body diagram. It needs to show the ramp with an angle. The black arrow straight down would represent the force of the weight, which automatically we will split into the perpendicular component and parallel component of weight. Remembering that we'll take the weight of the cart times the cosine of the angle. There'll be 3 different angles, so you'll do this 3 different times. And for the parallel component of weight, you'll take the weight of the cart times the sine of the angle. There is friction, so you will have a measurement for that. And then, of course, always there is the normal force of the ramp pushing back up on the cart. And that will be included in the sum of your perpendicular forces. As this cart obviously will be moving down the ramp, when you do your net force equations, it will be set equal to MA for the parallel, but still 0 for the vertical, because the cart will not jump on the ramp. The lab instructions will have you calculate the net force equation in the parallel. As you recall from the free body diagram, you have the force of friction, the parallel component of weight. Those are the only two parallel components. And there is motion, so we'll set it equal to MA. What you'll find from your data is that the force of friction will be about 0.3 newtons. This is where we find out if you watch the video, because if you didn't watch the video, you're not going to have these answers. And the weight is going to be like 2.6 newtons times the sine of whatever your angle is. And the angle will be different for each number of books that you use. And then that will be equal to now we need the mass of the cart. We can get the mass of the cart from the weight. So that'll be 0.26 kilograms times A. Now we can, once we know the angle, solve for A. We'll obviously do this 3 times because we're going to have 3 different angles. Let's see, don't forget that the force of weight will be negative there. That will affect your math. And then the last step will be to calculate your percent error. The experimental value will come from the computer data. You'll be recording all that in the data table. And then the accepted value is going to be the one that you do with the math from the net force equation. Don't forget to take the absolute value and multiply times 100, and then record the percent error in the data table. So you're going to do that for all 3 trials. Just make sure that for each of the 3, you use the corresponding computer number to the corresponding math number for acceleration. So all that should get you going on your lab. Even though I won't be there with you, you should be able to follow along with the lab instructions and then refer back to this video if necessary. My expectation is that you will complete the lab all 3 trials, complete the calculations, answer the final question, and submit to Edmodo before I see you on the next day. So, good luck.